Okay, this is part 2 of chapter 16 on acids and bases. Part 2 is actually picking up with section 16.5. I was working on that worksheet last time and we did the first 8 problems on the worksheet. So shortly we're going to do problems 9, 10, and 11 on that worksheet. Okay, and we start off in section 16.5 with weak acids and acid ionization constants. Last lecture, and I'm going to jump back through those slides. You guys have it in your notes. Last lecture, we listed all the strong acids, okay? And we listed strong bases. It's on 2 slides after this. But a weak acid is simply an acid that's not on this list. So usually what I do in the classroom, just to try to ask y'all differently and get you thinking differently, is I have you look at this list and I want you guys to name something, an acid, that's not on the list. Because if it's not on the list, it's going to be a weak acid. But since I don't get to hear the stuff you named, I'll name a weak acid, HF. Okay? And so what it means to be a weak acid, as we said, it doesn't completely ionize. And we can show that ionization of HF. And we did this, it was one of the first examples I used in your notes, I think. That was HCl for chapter 16. But if we show HF donating a proton and water accepting the proton, we see that these would be our products, okay? Because it's an equilibrium reaction, we know that again because it's a weak acid, it has an equilibrium constant expression. Products over reactants raised to the power of the coefficient. For this acid, the equilibrium constant expression K is equal to the products. Remember, we can write this as hydronium ion times fluoride ion. Or, remember hydronium and hydrogen are used interchangeably? We could write it like so. That the hydrogen ion times the fluoride ion, that's the products, divided by, and we remember that we don't include liquids, so the only thing that goes on the bottom of the ionization constant is the HF. And so this is how you would write a weak acid expression. These are labeled with a Ka, A meaning acid. Okay? There is a Ka table in your book on page 735. I'm about to move and take a picture of that. We do not memorize the Ka values. I actually have, and I'm going to show y'all. In my book, can y'all see over there on the right, that little yellow tab? It's labeled Ka. In my book, I have the page marked with a little piece of paper, with a little sticky note. A little bit later, there's a KB table, and I have it marked so that I can just flip back real quick and look these values up. Typically, on a test, I provide this table to you, and I will still provide that table to you somehow when you take your test. The table lists, this one in the book is a very sad little Ka table, actually, because it lists so few acids. But look, it provides you the formula, the name, even gives the Lewis structure, and it provides the Ka. Okay? So, for any of these acids, you should be able to write an expression like this, and this expression, and also to write the equilibrium reaction for what's going on. Okay? So, let's work with... HF is actually one of the examples on the worksheet, so I'm going to pick a different one to show you how to work it. Let's calculate the pH of 0.124 molar nitrous acid. Okay? First of all, you guys are going to have to know nitrous is not a strong acid. If it said nitric acid, that would be a strong acid. That means the hydrogen ion concentration is 0.124. But it's nitrous acid. So again, I'm going to show you how to work this with an ice table. You could look at your Ka table in your book and find nitrous acid and it's Ka. 4.5 times 10 to the minus 4, and nitrous acid is HNO2. And so we know the Ka, I'm going to go ahead and write that down, is 4.5 times 10 to the minus 4. And nitrous acid is HNO2. And so if I'm writing the equilibrium expression, I'm going to do it without water because I know the water is not included in the Ka. Then I know this reaction shows the partial ionization of nitrous acid. I'm going to set up an ice table. And unlike last time when we did strong acids, this is truly an ice table because the final line is equilibrium. The problem tells me I have 0.124 nitrous acid, so I know I'm starting with 0.124 molar nitrous acid. And y'all will remember from learning equilibrium that I'm not starting with any of these initially. Okay? Now, it's not strong, so we cannot say 0.124 right here because it doesn't completely. It partially ionizes. So what we have to say is, well, X amount ionizes. And you're familiar with using X's on these ice tables. And that's how the ice table is completed. We looked up the Ka. We know that the expression for this acid would look like this, that the hydrogen ion concentration times the concentration of the nitrite ion divided by the concentration of the HNO2. And so now I'm going to plug in the numbers. The Ka is 4.5 times 10 to the minus 4. Guys, the hydrogen ion concentration at equilibrium is X, and the nitrite ion equilibrium concentration is X. So instead of breaking it down and saying X times X, I'm going to go ahead and just write X squared. And on the bottom, I'm going to write 0.124 minus X. You cannot take the square root of both sides of this like we did in the equilibrium, because we don't want to take the square root of that denominator. So instead, what we're going to do, because right now as this is set up, it's going to end up taking us to quadratic equation. We don't want to do that. So what you can do every time you have a weak acid, guys, we're going to assume that X is a small number. We're going to assume that it's so small that we don't have to worry about it there. So we're just going, even though it's here in the ice table, we're going to pretend it's not there in the math. And I'm going to solve for X. How do I do that? I'm going to cross multiply, then I'm going to take the square root of it, and that'll tell me what X is. So pause the video and solve for X. Okay, when I solve for X, I got 7.47 times 10 to the minus 3 molar. That's what I got for X. What is X telling you? Well, this is the one that's important. X tells you the concentration of the hydrogen ion. So the concentration of the hydrogen ion is 7.47 times 10 to the minus 3 molar. You'll remember that the pH is the negative log of the concentration of the hydrogen ion. So the negative log of that gives me the pH, which is 2.13. And that answers the question. Okay, let's take this a step further. And let's talk about this little assumption we made over here where we just marked that X out. How can that be okay? Well, there's something we can calculate, and it's called percent ionization. Now think about that, and it makes sense. What percent of it ionized? So percents, y'all know it's the part divided by the whole. So to calculate the percent ionization, the part that ionized is the hydrogen ion concentration, or the X. The whole is the initial concentration of the acid, and then multiply it by 100%. So in other words, the percent ionization, for the one we just did, the hydrogen ion concentration is 7.47 times 10 to the minus 3. The initial concentration of our acid was 0.124 times 100%. We're going to calculate that. And so the percent ionization for this one, it's 6% ionized. And so that's a little high in that. Typically, to forget about this little minus X, you want it to be about 5% or less, okay? And so the pH of this is probably a little bit lower than 2.13 in all actuality, but I'm not going to make them over 5% ionized on the test so that we don't have to do quadratic, okay? Let's work another one that's a pH of a weak acid that's not on your handout sheet that I gave you. And let's do percent ionization. So let's calculate the pH and the percent ionization for, we're going to do the benzoic acid one. Let's do 0.185 molar benzoic acid. Okay. And you've got your Ka table in your book, but we can look, I'll flip back and you can write it down. The benzoic acid, there's the formula, there's the Ka. Now, we're going to want to set up a reaction and do an ice table. But let me show you something. Y'all wrote down the formula, C6H5COOH. So you can do this, C6H5COOH. You know it's equilibrium because it's a weak acid. Guys, anything that's coming off of that Ka table has to be a weak acid. So you can write it like so. Okay, but what a lot of times I'll do on these, instead of writing the actual formula, is I will just say HA is just the weak acid. And I'm going to actually put it in a different order than what I have there. And I do it like so, okay? Because the formula is not going to be important for solving this problem. Again, I'm going to set up an ice table. And you guys pause the video and set up the ice table. Okay, then check what I have. And then once you restart the video, hopefully this is what you did for your ice table. Okay, we have the Ka. We know what the expression looks like. So, guys, won't that be that the Ka is equal to X times X, which is X squared, divided by the initial concentration, which is 0.185 minus X, and we're still going to just not even include that in the calculation. We know that the Ka is 6.5 times 10 to the minus 5. Do you see that we're ending up the same place on these weak acids every time? The weak acids every time brings you, once you do the ice table, that the Ka is equal to the X squared divided by the initial concentration of the acid minus the X, which we eliminate. So you do not have to show me the ice table every time. You can omit showing this if you see how to get here. Okay, so pause the video, solve for X, calculate the pH and the percent ionization. Did you guys get 3.47 times 10 to the minus 3 molar? for X. Okay. Again, X is the hydrogen ion concentration, so pause it and figure out your pH. pH is simply the negative log of that number. Do you guys get 2.46? Again, that's the negative log of 3.47 times 10 to the minus 3. Okay, pause the video. Calculate your percent ionization. I got 1.9% for my ionization. And I simply said 3.47 times 10 to the minus 3 divided by 0.185 and times 100%. Okay? So there's the pH and there's the percent ionization. And now we are ready to do numbers 9, 10, and 11 on that worksheet. I will say, let's see, number 9 is acetic acid. That Ka is in your book. 11 is hydrofluoric. That Ka is in your book. 10 is propionic acid. So what I'm going to do is Google the Ka for propionic acid, and I'll have those written on the next slide. Okay, so here are the last 3 problems on that worksheet I gave you. 0.573 molar, 0.26, just making sure I wrote them down correctly. This is the Ka I just Googled because it's not in the book. The book just has such a small table for that. Okay, and if we're following along with this worksheet, the worksheet was asking us to calculate each of these. Okay, so I'm going to do acetic acid first. I'm going to jump to the next slide and then come back over here to fill in the answer. And so to work number 9, we are going to say that 1.8 times 10 to the minus 5 is equal to x squared divided by 0.573. And guys, you feel free to write more than what I'm writing so that you understand how to work it. Okay, but this is just showing you the solution to it. Okay. Again, I'm getting rid of the little minus x. So for x, I got 3.2 times 10 to the minus 3 molar. Okay, X is the hydrogen ion concentration, 3.2 times 10 to the minus 3 molar. And so now I can calculate each of these because the negative log of that will give me the pH. (14) minus that gives me the pOH. Okay, and how I calculate the hydroxide, I can either say Kw divided by the hydrogen ion to give me the hydroxide. That's one way. Or I can say 10 raised to the negative 11.51. 10 raised to the negative pOH. Either way will give me this answer. And I'm remembering to check that if this is raised to the negative 3, my pH ought to be around 3. This is negative 12. pOH ought to be around 12. Okay? So now you work numbers 10 and 11. Okay, there's the answers for number 10. Is that what you got? I'm going to write the work down here. I said the Ka, 1.34 times 10 to the minus 5 is equal to x squared divided by 0.267. Cross multiply, then take the square root. And that's what I got for x, 1.89 times 10 to the minus 3. Okay, now pause the video and you work the HF. Okay, those should be your answers for number 11. So check that and pause it and see if there's any mistakes, if you can find them. where you can ask, post questions on the video or email or what have you. Okay, and I should point out too, y'all, like I do 10 raised to the negative 11.77, and that gives me the OH. If, on the other hand, you're saying the KW divided by the H to get here, let's see, I don't even calculate it that way. Like, punched it in wrong, divided by. Your answer varies. Like when you do it this method, you get 1.72 times 10 to the minus 12. And so, y'all, that's not a wrong answer. It's fine. Look, we're times 10 to the minus 12. So we're talking about 0.000. You got 11 zeros and then 1 7. So if there's little bitty changes in these decimals, like 5.81 versus 5.83, that's fine. Also, on these, when I calculate the X, like when I first get this, and I take the negative log of it to get the pH, I actually don't take the negative log of 5.8 times 10 to the minus 3. I take the negative log of the answer that's still in my calculator. Okay, so if you're rounding off, yours is going to be a little different. It's not wrong. It's just that you're rounding, so don't worry about that. And if that doesn't make sense, or if you have more questions and want to see if things are still okay, then y'all can just ask. Again, email me, message me on Canvas, or put it at the bottom of this. That's fine. Okay. A little bit. Let's go in on each of these. Just for practice, let's calculate the percent ionization. Remember how to do that? For the percent ionization, you take the hydrogen ion, divide it by the initial concentration, and multiply by 100%. So calculate the percent on each of these, just so we can practice that together. Okay, so that's what I got for each percent ionization. Number 11 is really too high to do the little minus X thing, but because of the situation we have here of me not being there to show you and work through it, we are not going to worry about those high percent ionizations. Okay? Okay, before I introduce the next thing, it's going to we're going to use information you already know. So I want to remind you guys of what you already know. Went back to the benzoic acid one, the second one we did. And I want to remind you that we go here every time on a weak acid. That the Ka is equal to X squared divided by the initial concentration of the acid, and there's a little minus X there. Okay, so we're going to keep that in mind to work this next problem. Okay, so I'm actually going to pull one out of your book, sample problem 16.14, to work, which is, it's about aspirin, and aspirin is acetyl salicylic acid, okay? Aspirin, it's a weak acid. One of the labs I wanted to do with you guys is have you guys make aspirin, but we're not going to get to do that. A 0.10 molar aspirin solution has a pH of 2.27. Calculate the Ka. Okay, and this is different because we've been looking up Kas and calculating pH, but this gives pH and calculates Ka. So, weak acid, they end up the same way every time. Remember that? You have to remember that, because if you don't remember how to do it, you're going to have to do an ice table to get to that point. Ka is equal to x squared divided by the initial concentration of the acid minus x. In this problem, we're going to calculate the Ka. What is x? We don't have a number for x right now, but if you look back, every time we calculate the x is the hydrogen ion concentration every time. I'm going to jump back to a previous slide. Here's where I worked the first one from the worksheet. But y'all, x is the hydrogen ion concentration every time. If we have the pH, and we do, 10 raised to the negative pH will give us the hydrogen ion concentration, which is the x. So, 10 raised to the negative 2.27 is x, which is 5.37 times 10 to the minus 3. So that means that the x is 5.37 times 10 to the minus 3. That's squared. That's the little minus x at the bottom. We can include it in this one. It's not going to bring us to quadratic. We know the x. And this little thing here is the initial concentration, which is 0.1 molar. And so that's all. We just have to do that math to solve for x. So be careful with it. Be sure you square the 5.37 times 10 minus 3. When you put the information in the bottom, you're going to want to put parentheses around it so that you don't mess up on your order of operation. And I get that the Ka is around 3.05 times 10 to the minus 4. And I didn't ask this earlier, but what are the units of Ka? If you'll remember, equilibrium constants do not have units. Okay? And so that is sample problem 16.14 from your book. It's on page 743 if you're using the 5th edition. There's some practice problems under that and some checkpoints. If you guys wanted to, use those for more practice. Connect's going to practice them, etc. Now, we started this lecture today, didn't we, doing 16.5? Y'all, we just finished section 16.5. Okay, it's a meaty little section, but it's not hard. Now I want to move on to section 16.6. Everything we've done so far has been weak acids. 16.6 is weak bases and their ionization constants. Okay, and y'all, weak bases, they look funny. In your book on page 744, there is a table of ionization constants for weak bases, okay? And so I said weak bases look funny. Y'all, it's going to be things you're not familiar with. Ammonia, yeah, but look at those formulas and look at those names. Okay, these are, they're organic compounds, every one of them. So that's what I mean by they look funny. It's just formulas you're not used to writing. You do not memorize these, okay? You have this table. But let's do one, let's pick out methylamine, CH3NH2, okay? It's a base. Bases accept protons. So can you guys show this reacting with water and show it accepting the proton from water? Pause it and write that, and then check what you got. Okay, what you have. Notice this methylamine started off neutral. When I put a proton on that, it's going to make it positive. Okay, if I were to take one of these hydrogens off and just write NH, that's going to make it negative. Okay, because hydrogens have a positive charge. So just to point that out. Okay, this has a Kb expression, products over reactants raised to the power of the coefficient. That expression, I'm going to write it here because I'm going to put an ice table under it in a minute. So the Kb expression would be products over reactants. Raise the power of the coefficient. Again, I'm not including water in this. Okay? So let's add this. Let's make it a problem, something we can calculate. Let's calculate the pH of 0.085 molar methylamine. Okay? All the other information we have on this slide we would have got from the table. What else are we going to need to go back to that table and get? We need to get the KB. KB for methylamine, 4.4 times 10 to the minus 4. Okay? Let's take this problem and put stuff in the ice table. 0.085 is our initial concentration. We don't have to worry about the water because it's a liquid. Initially, we're starting with none of the conjugate acid and no hydroxide. So guys, this is going to ionize like so with the X's. At equilibrium, we're going to have 0.085 minus X, X, and X. So now I'm going to take these and the KB, and I'm going to combine them all into this expression. So I'm going to say the KB, 4.4 times 10 to the minus 4, is equal to X and X, which is X squared, divided by the initial concentration. That's looking familiar, isn't it? We're going to pretend this is small, and we're going to solve for X. Cross multiply, take the square root. Pause the video and solve for X. You should get 6.12 times 10 to the minus 3 molar for X. Okay, now stop here. That is the number for X. But what is X telling you? Look at the ice table. X tells you the concentration of the hydroxide ion. So when you take the negative log of the X, that's going to give you the POH. The POH is 2.21. What did I ask for? I asked for the pH. How do you go from the POH to the pH? You can say 14 minus 2.21, and that gives you a pH of 11.79. That's the answer. So, to clarify, there's an extra step when you're dealing with the base, because X is the hydroxide ion concentration. So you've got to go through the POH to get to the pH. How do you keep that straight? Y'all, anytime you're using a KB, how do you know if you're using a KB? I'm going to jump slides. You know because the table tells you it's a KB. Anytime you use a KB, X is always equal to the hydroxide. Anytime you use a Ka, X is always equal to the concentration of the hydrogen. Okay? I only worked one of these, but there's more practices in your book. Let's see, that was the end of section 16.6. So on page 745, there's sample 16.16. And then on page 746, 16.16 is continued. And then there's some checkpoints for you if you want to practice those. Again, you're going to get practice on Connect, but it's the checkpoint for section 16.6. Okay? And that will complete Lecture 2 of Chapter 16.